That is usually, except sometimes it doesn't connect. What did you get? 0.0038 seconds. Well, that makes sense, doesn't it? Because it's not going to be a long time that the dart's being slowed down to a stop. Now we can get A. We can get A from delta V over delta T. And delta V is minus 21 divided by 0.0038 minus 5,526 meters per second squared. So that dart is under around 550 Gs of acceleration it's experiencing as it slows down. So now we have our acceleration. We can come up here and see what that net force is. Because we'll take it up and plug it in and use it up here. So 0.005 kilograms times 5,526 meters per second squared. The negative would just mean that it's acting back against the, slowing it down. .6. What's my units? Newtons, right? That's good. Do I need to go up? Did you get that all down? Okay, the next problem, 2. So these Atwood machines, you know, we started to work a little bit on them, but we, you know, we need some practice with them, right? So that's what we'll do. But we'll do a number of these problems a couple different ways. We'll do them first with the forces, and then later we'll do them with energy as well, using potential and kinetic energies. So in this problem, number 2 says an Atwood machine is set up with a mass of 10 kilograms and a mass of 9 kilograms. Find the tension in the string and the acceleration of the system. So remember, the Atwood machine was just on a pulley, and it had a very simple machine where the masses are unequal, and the heavier mass will go down and the lighter mass will go up, right? Like Murphy, right? Why I wasn't at work today, right? Remember that song? So now it's going to be going through my head again. So, all right. So let's draw a little simple figure for this. We'll have a 10 kilogram mass and a 9 kilogram mass. Which way will this move? Down, and this will go up, right? So the first thing to do is to draw some free body diagrams for each of them. So with a 10 kilogram, what forces do we have acting on it? We have an Fg down. And we also have what? Ft up. Okay. Now how did I know that Fg was bigger than Ft? Right, because it's a bigger mass and it's going to move down. So that means for the 9 kilogram over here, its Fg is going to be smaller, and it must be smaller than what? Because it's moving up, so it must be smaller than Ft. But we know the Ft's are what? They're equal, so that's the key. and they're both accelerating at the same. So you have two sum of the forces here. You got one for the 10 kilogram and another one for the 9 kilogram. What's the winner and loser for the 10 kilogram? FG is the winner minus FT, which is losing in that situation, equals mass times acceleration. What's the winner and loser for the 9 kilogram? Tension's the winner minus the weight force equals mass times acceleration. Now we just plug in what we know. Well, if our mass is 10, what's our FG? 100 newtons. We don't know FT yet. But that's the mass that's accelerating is what? 10 kilograms, right? We don't know the acceleration. One equation, two unknowns. We must be able to get more out of this equation. FT, what's my FG here? 90 newtons. 9 kilograms times A, because that's the 9 kilogram mass accelerating. Is that clear to everybody, or are there parts that are extremely unclear? I'll take that as everybody has it 100%. Right, Paul? With some practice. Well, what do we have to do now, though? Isolate FT. Solve. So FT from this one would be 9 kilograms times A plus 90 newtons. And then we could plug it in up here. I'll write it down here, though. I'll rewrite it over here. So it would be 100 newtons. Don't forget, like, to distribute, because we're going to plug this in now. 9 kilograms. So I'm plugging it in for this FT, okay? And I don't want to forget to distribute the negative. Now we have one unknown, which is A, so we'll be able to go. I'll just use black now. See what I almost did? Um, 100 minus 90 is 10. Add the 9 over. A will be 10 newtons over 19 kilograms, right? Or 0.53, what's my units? That's right, because a newton is kilograms times meters per second squared, so the kilograms cancel, and I'm left with an acceleration of 0.5 meters per second squared. So now, to get the tension, since it asks for that, it says find the tension and the acceleration. I can come back up to this formula and plug it in there, and I'll get FT is 9 kilograms times 0.53 meters per second squared plus 90 newtons. 4.77. Okay, so that's an Atwood machine to find the acceleration and the tension force. Yeah, right? Because the one's going to accelerate down this way and the one's going to accelerate up. Well, what it really is like one's going down, yes, and one's going up. But if you took it and put it in a straight line, they're both accelerating the same way. So, by using like the free body diagrams and the larger one minus the smaller one, we can see what all directions are from this, our free body diagrams. We can see all the directions of the forces, and because we know the net force would be this way here, and the net force would be that way here, we also know what the directions of the accelerations are. So that's where that direction comes in. Okay. Number 3, on that same page, 11 of 18. So this is a 5.3 problem. So remember last time, did you do your 5.3 notes? Okay. I don't know if I checked them, but I'll check them on tomorrow with your 5.4 if I haven't done it. So if you haven't done them, I think maybe I did check them for you though. Huh? Chunky dynamics, yeah. Well, you were seldom here the last week. How'd you guys do? So how come we hear about like how the boys do, but you don't get up and tell us how the girls do? Oh, was it early? Oh, you know what? I was talking to somebody and not paying attention. It's my fault. Really? I went to the UB women's basketball game over break and brought the kids and stuff. And Sloan Walton was on it, and she was a student of mine. I didn't know she played. She's a basketball player, so they were pretty good. They blew out some team. I don't even know who it was. Roberts? Maybe, I don't know. It just said Robert on this front. I was just there for the hot pretzel, but it was good. All right. What's that? Okay. Oh, when is the Prep C game? That was the other thing. On Wednesday? That would be fun if I can make it. I don't know. Those afternoons, maybe part of it at least. All right, so that's a table. On the table sits a block. And there's a couple of pulleys involved. Some of you will do stuff like this and we set up the large force lab. Or, you know, like where we break up and do different things. Trying to get this to go right. So there, it's set up like that, and then hanging from that is another 10 kilogram mass. Okay. It's connected to the bottom of this pulley. Oh yeah. It's going to move, this whole thing's going to move and accelerate down. Yeah, yes. See, this connects around on a rope. This is just a table. It's a little thick. Yeah, so the rope is around here, and it's connected to this one. It goes around the pulley to that. So when we let it go, the 10 kilogram block is going to move down, and the 3 kilogram block is going to move over. And it's not in equilibrium. It's going to accelerate until the 3 kilogram block knocks the pulley down and collapses. This, it will just pull down. This 3 kilogram block is going to move this way, and this is going to move down. It rolls. This rolls. So this is just floating in free space because it's got the rope on it. What? Yeah, I know, but that's all right. It just means putting. So let's get to the free body diagram for these. So as this goes, the rope this is going to move this way. This is going to move down. So as this moves down, okay, it's going to move down half the distance that this moves over. Although that's not really important for this problem. Just if you see like this amount is going to be broken up equally in these two ropes here, so that will also move down like that. Not as much as this moves over. Half this amount it will move down. So, and I see how it seems a little weird how this is floating out in space, but it's the rope that it's and the tension that's going to hold that up. Okay. So let's do the free body diagram for this one. FG down and what's up? We would have friction, right? But let's read the problem. It says 10 kilogram block, tension in the rope, acceleration, no friction. But I could easily add friction, on your test or something. But that wouldn't be a big deal because you know how to work with it, right? It would just be part of your free body diagram. Oh, let's make it green. So this pull here is the tension in the rope with no friction. Let's go to the 10 kilogram block. What forces do we have on that? Fg and what else? Tension, but how many tensions do we have? 2. So we have an Ft and an Ft. The same Ft, but we have 2 of them. Yeah. Same rope. Well, they're actually probably not equal because of the tension in the pulleys, or the friction on the pulleys, I'm sorry. And the pulleys. So in that sense, yeah, no, but for us they'll be equal. Yes. And in actual they're close, huh? No, the tension would still be equal. We would just have a friction over here, which would affect the acceleration of the overall system. All right, so it's beginning. Oh, we better get out of here. Look at that snow. Did anyone see the day after tomorrow? This is called an Arctic vortex that's coming down. Polar vortex, you're right, actually. Oh, good question. Okay, yeah. So tomorrow is likely, well, I don't know. We got a pretty good shot that we won't have school, but we might. You never know. I would. All right. I have no idea. The thing is tonight you should prepare for school tomorrow anyways, and if you get an extra day to study for exams, that's great for tomorrow, right? So tonight you're going to get all your homework done that you need to do. You're going to watch your video. You're going to do all that. And so if you did have a snow day tomorrow, that should pretty much secure nice 85s to 100 on all exams, right? Because that gives you 16 hours to study. Maybe a little Wii golf in there or something. Although I don't play that anymore. I had to cut myself off. No, I'm just kidding. So, but anyways, what was I talking about? Oh yes, day 7 is tomorrow. Okay, but because you prepared for tomorrow's classes, and we're on a rotating schedule, right? You could, if we came back just to day 1, you might have not brought home the books for F block, right? Because there's no F block on day 1. So, like, tonight you may not have brought home your F block stuff, and you could come back, or well, whatever, however it works out. And so when we come back on Wednesday, it's not going to be a day 1, it's going to be a day 7, okay? On Thursday, we'll be back to regular day 2, so it's day 1 that we actually miss. It makes sense. Yes, Mr. Coburn came up with this years ago, because we used to come in, it was missed, and he said, why don't we come back and come into and do a day, skip the other day and come back to that one, because all the students were preparing for, tonight you'll be preparing for day 7, right? So it makes sense to come back for a day 7. You weren't preparing for day 1. You know, and you know how, like, you would come back and your history teachers would, if you came back and it was actual day 1, they said, well, it would be a test. I have a test for you, right? Because I posted on Schoology this morning at 3 a.m. Oh, I'm just kidding. Anyways, let's do this problem. Distracting me. All right, we sum the forces, okay? Same sort of thing. Sum the forces equals mass times acceleration for that one. And then the sum of the forces equals mass times acceleration for this one. And in this case, the only force, the winner, is Ft because there's not even a friction. But if there was friction, and you'd have to be given mu or something to get it, you would have minus Ff, but we don't have that here. So equals the mass, which is 3 kilograms, times A. 2 unknowns, but we're going to have 2 equations, right? So over here, what's my winner in this direction? Fg, that's right. Minus, what are my 2 losers? 2 Ft's, right? So we can just put those together, it's 2 Ft's. Loser in the force side, tension itself. Fine, 10 kilograms times A, and now we know Ft is also 3 kilograms A from over here, so we can put that right in here. So plugging in this to that is Fg minus 2, 3 kilograms times A equals 10 kilograms times A. This is minus 6. Oh, the Fg we know too, don't we? I left that out. I'm sorry. What's Fg here? 100 newtons. Minus 6 kilograms A, 10 kilograms A. So 100 newtons equals 16 kilograms A. A is 100 newtons divided by 16 kilograms. 5 something, right? Oh, 6 something. 6.25 meters per second squared. Okay? And then once you have A, you can go back over here and get Ft. And Ft is 3 kilograms times the 6.25 meters per second squared, or 18.75, right? 18.75 newtons. Okay? So the bell's going to ring in 1 minute. Well, 55 seconds. So have a nice one-day weekend, maybe. Oh. What are you learning in science? Earth science? General science? Wind turbines? We do anything with that? Biology? What are you studying right now? Rocks. Okay. See, that's earth science. Yeah.